Guys, Paper Pilot back with another video. Today we are going to be solving paper 2 of 9709 Physics, paper 2 AS, February March 2026. You guys should have your exam on 20th May. That's why I'm trying to make this video as fast as possible so you guys can learn a lot about this. So this is a solution video, right? So the first question we have is define force. All right, so the definition of force is very simple. It is the rate of change in momentum. That's the official definition. You don't have to write anything else, just write this. Easy one mark, right? Okay, so the next question says use the definition 1a to show the SI base units of force are kg. Okay, so what is force? Force is basically energy by time, right? And energy base unit, I have it memorized. You guys should keep it memorized. It is kg meter square s to the power minus 2, and time is s. So if you divide this, you get kg meter square s to the power minus wait, energy equals to, yeah, wait a second, force is this kg meter. Okay, wait, maybe I'm okay, hold on. We have to use the definition, right? Okay, we cannot not do like this. We have to use the definition. Alright, so rate of change of momentum basically means this, which means m by v by t. Mass into velocity, okay, divided by time, which is s. Alright, which leads to be m s to the power minus 1 equals to kg meter s to the power minus. Okay, yeah, that's how you do it. Alright. Shown. Okay. Alright. Easy enough. Now, a student is investigating this relationship between the force applied to the piston of a syringe and the velocity of fluid exiting the syringe. The student wishes to use the equation V equals to Fk by Ma, where V is the velocity, F is the force, K is the constant, okay? M is the mass of the fluid, and A is the cross-section area. By considering SI base units on both sides of the equation, state and explain whether this equation is homogeneous. Okay, so homogeneous means both of them, if we equate the SI base units, it should cancel out, right? Okay, we have to state and explain whether it is homogeneous or not. Okay, so if it cancels out on each side or ends up with 1 and so ends up with the same value, that means it is homogeneous. If this does not cancel out, that means it's heterogeneous. Okay, so velocity, right? V equals to Fk by Ma. Velocity is meter per second. Force, we already figured out, is kg m s to the power minus 2. And K is given here as this. Meter square s to the power minus 1 divided by m mass, so kg, into the cross-section area, which is meter square. Now let's cancel all this. Boom, boom. And okay, which leads to be meter s minus 3, and they are not equals to. Hence, it is not homogeneous. So we're gonna write that it is not a homogeneous equation, as units on both sides are not equal. Okay? Alright. Now, state the principle of conservation of momentum. Okay, this is very simple. So it is in a isolated system, the total momentum before collision is equal to the total momentum after collision, right? Nice. Now, a stationary boat of mass 160 kg floats on water. The mast of the boat is vertical. A sack of mass 23 kgs is thrown at the boat. Okay, as shown as figure. Okay, this is the mass of the boat is a sack. Okay, it's dropped. All right. So immediately before colliding with the mass of the boat, the sack is traveling horizontally with a speed of this. The sack collides with the mass and remains in contact with its mass without rebounding. Assume that the resistive forces acting on the boat during the collision are negligible. Calculate the horizontal speed v of the sack and boat immediately after the collision. Okay. So, total momentum before collision is equal to total momentum after collision. Which basically means this. 1 plus m2u2 is equals to m1 plus m2v. Okay. So before collision, the mass is traveling with a speed of 3.4, while this is stationary, so we don't have to include that. And after collision, they're both gonna be added up because they're both gonna be in contact. Hence, the mass will add up plus 160, right? And we have to find out the velocity at which this travels in. Okay, so now just solve for v, and just use a calculator. 78.2 divided by 23 plus this, which is 183. Okay, so if you divide this, we get 0.427. Now you have to write this in 2SF. Always 2SF, guys, unless the question specifies this has to be in 2SF. So 0.43. Okay, now the total kinetic energy of the sack and the boat immediately before the collision is E1. The total kinetic energy of the sack and the boat immediately after the collision is E2. Okay, determine the ratio E2 by E1. So before collision, the speed is this, half into formula for kinetic energy. I think all of you should know this, half mv squared. So half into the mass 183 into after the collision, which is 0.42, we just figured out, squared divided by before. So before the mass was 23, so just write the same thing except with the mass different, the speed is different. 3.4 squared, this cancels out, and just use the calculator. And we get 0.127, which we round off to 2SF is 0.13. Okay, state and explain whether the collision between the sack and the boat is elastic or not inelastic. It's inelastic because the kinetic energies are not the same. If it was for elastic, right? For elastic collision, total kinetic energy before must be equals to the after, right? For kinetic energy. But in this case, it is not. Hence, it's an inelastic collision as the total kinetic energy to the total kinetic energy after collision. Okay, Right, now wait guys, it's coming back, just give me a second. Alright, so the next question is number C. After a short period, the boat in 2P is at rest again. Show that the upthrust acting on the boat with a sack is 1,800 newtons. Okay. It has rest again, that means it is at equilibrium. Since it's at equilibrium, that means the weight is equal to the upthrust. Okay. So upthrust is basically equals to the weight, right? Which means upthrust is equals to mg because that's the formula for weight. Hence, upthrust is 183, which is total weight, into 9.81, which comes out to be 1009. Okay, very simple. Nice. Shown. Okay, next question. The boat displaces water with a volume of this. Calculate the density of the water, give your answer to 3SF. Okay, so here it literally specifies 3SF, so don't write with 2SF for this question because it literally specifies it. So, density. What's the formula for density? Density, but we have to find the density of the boat. No, density of the water. Okay, that means we cannot just use density equals mass by volume. That is not going to work here. But the formula for upthrust is rho Vg, which means density of the liquid and volume of the liquid displaced. And this is just 9.81 gravitational potential, gravitational unit. Okay, so upthrust we know is 1800, and density we have to figure out. Volume we know is 1.80 into 10 to the power 5, and G is constant 9.81. So if you rearrange this, we get hold up, wait a second. Okay, wait. There's still something we need to do here. Now, this might caught off guard some students. Okay, so here it's in cm cube, the volume, while the answer is in meter cube. So to convert from cm cube to meter cube, how can we convert it? Basically, we divide that by 10 to the power 6. So 1.80 into 10 to the power 5 divided by 10 to the power 6, we get 0.18 meter cube. And now we put that in here, not this, sorry. Now if we solve for density, we get this, which is the answer, 1020. Okay. Alright. Moving on, we have, I think this is another force question. Alright. A roller coaster carriage of mass 280 kgs travels over a raised section of track. Okay. This is the carriage, it's going up and down. Okay. So at position X, the carriage has this kinetic energy. It's in kilojoules. Okay. At position Y, the carriage has a kinetic energy of this. Okay. The length of the track between X and Y is this. We have given the distance between X and Y. All right. So in moving from X to Y, the carriage does 5.1 kilojoules of work against the resistive forces. Calculate the average resistive forces acting on the carriage between X and Y. Okay. So energy is given. So whenever you see the word resistive forces, just use this formula. Work done is force into perpendicular distance, direction of the force. Okay. And if we rearrange that, we get force equals to work done by distance. Okay. So the work done given is 5.1 into 10 to the power 3. Since it's kilojoules, convert to joules, and the distance given is 23, which we get as 221.73. Okay, nice. Round it off to 2SF, 220. Now, calculate the change in height between x and y. Between x and y. So when the carriage is moving up, like up the hill, right, up the racetrack, its speed is gonna decrease while its gravitational potential energy will increase, right? And we're given the kinetic energy at like the starting point and the ending point. So the kinetic energy at the ending point, which is y, is 1.3. Okay, so we have to find a change in height. Since using the conservation of law of energy, we can basically see that we can form an equation. So basically the kinetic energy at x should be equal to kinetic energy at y. Okay. So how can we do this? So the kinetic energy K, let's say, is kinetic energy of K plus gravitational potential energy plus which we get from the length, which basically means this part. Okay. Change in height. So initially at x, it's 16.1 kilojoules. So let's write 16.1 kilojoules times 10 to the power 3. That will be equals to the kinetic energy the carriage has at y. Okay, we have to add that. So 1.3 into 10 to the power 3 plus the gravitational potential energy, which we're just gonna write mgh. And this is the h here is what we need to figure out. Plus this energy that's dissipated here, which was 5.1. So 5.1 into the power 3. Okay, mass we already know is given here, right? Mass is 280. 280 into 9.81 into h. Okay, this is... Now we have to solve for h, which comes out... it's a calculator. Okay, so h 9.7 to 10 to the power 3 divided by 2746.8, which roughly comes out to be 3.53 meters. 3SF, 2SF, so 3.5. Okay. Now the carriage travels further along the track to point Z, which is this part right here. State and explain whether the speed of the carriage at Z is greater than, less than, or same as the speed of the carriage at X. So at X, it's already traveling at a good speed, and at Z, okay, it increases, the gravitational potential increases. Okay, so at Y we already figured out. Okay, so from here to here, the overall energy will increase, but over here GP decreases. And what about the speed? What about the speed at S? The overall kinetic energy of Z will be lower. And if the kinetic energy at Z is lower, because over here at X it's already moving at a speed, but at Z it's like about to stop. That means kinetic energy is lower, and it says the carriage travels further along the Z to point Z, which basically means that at point Z it stops, right? That means its speed is decreasing, it's decelerating. All right, So the kinetic energy at Z is lower, and if the kinetic energy is lower, speed is of course lower. Hence, the speed at Z will be lower than the speed at X, as kinetic energy at Z is less than at X. Well, it says less, alright? It's less. Okay. I hope you guys understood that, right? Alright, now, number 4. This one seems a bit tricky. A uniform square picture is attached to a wire and hangs in equilibrium from a pin at point P. Okay, this is point P, as shown in figure 4.1. The picture has a weight 19. Okay, so this is at the center of gravity. Okay, and the center of gravity is directly below P. Okay, so it's directly below P. It says the top of the picture is horizontal and the wire forms an angle theta with the horizontal. Okay, so forms an angle theta, and the tension in the wire is 13 newtons. Okay, so as we already have theta here, we can just divide this in. This is t sine theta, this is t sine theta, this is t cos theta, and this is t cos theta. Okay, and the tension is 13. Okay, so this is 13 sine theta, 13 cos theta, 13 sine theta, 13 cos theta. Okay. It says define the moment of a force about. Okay, that's easy. It's basically the product of force and perpendicular distance from the pivot. That is the definition. You guys can write from a point as well, but I like to say it's a pivot. Now explain why the moment of the weight about P is 0. The reason it's 0 is because the center of gravity is directly below here. The weight is directly below P. Right, and where is the pivot? Pivot is at P. Okay, basically the pivot, the weight is directly below the pivot. Hence, no force can produce a moment to like act about a pivot, right? Because it's directly below, the force is acting like down below, vertically down. So like you cannot move it about its like, you cannot move it about P. So the weight is directly below the center of gravity. No, it's below P. Hence no force can produce a moment. On the pivot. Okay, it's directly below, hence why it cannot. If it was somewhere else, not directly below, then yeah, it could have, caused a moment. But it's directly below the pivot. P is the pivot here, right? And the weight is directly vertically below. It passes through. The force passes through it. Hence, it cannot produce a moment. Now, calculate theta. Okay. This one should be fairly easy, actually. We know T is this, and we know T is this. Okay, so we can just... The weight is 19. And it's at equilibrium. That means this and this, if we add them up, it should equal to 19. Which basically means that T sine theta plus T sine theta Add them up, it should be equals to 19. So 2 into 13 sine theta is equals to 19. And sine theta comes out to be 19 by 27. Theta is 46.95. Round them up to 2SF is 47. Okay. Now, a wire has a diameter 0.8 millimeters, and it's made of metal with Young modulus. The wire of Ace-Hooke's law. It says calculate the strain. So, what is strain? Strain is basically the ratio of, not the ratio, more like just the formula is divided. Like, it is extension by original length. In this case, we are not given either of those things, but we are given the Young modulus, and the formula for Young modulus is stress over strain, which we can just simplify as FL over AX. F is the force, L is the length, A is the cross-sectional area, and X is the extension. So the Young modulus is given, a diameter is given, which means the area is given, and we are trying to find the wire X. Okay, strain. We don't know what the strain is. We do know the force, that means the tension is 13. Oh, okay, there is a easier way to do this. I figured it out. So we can just find stress and then substitute in this formula. Formula for stress is the same as pressure. Force by area. Force is 13, area by r squared, but it's 0.8, so to convert that, 0.80 by 200, 2000, divided by 2 divided by 1000, whole square. Okay. So if we do this, we get 25.85 into 10 to the power 6. So extension is 25.85 10 to the power 6 divided by x, and the Young modulus given is Young modulus given is 9.3 into 10 to the power 10. If you rearrange this, your strain comes out to be 2.77 into 10 to the power minus 4, which, if you round up to 2SF, is 2.8 into 10 to the power minus 4. That is the answer. Okay. Now, the bottom side of the picture shown in figure 4.1 is 1.6 meters above the ground. So the ground is, let's say the ground is somewhere around here. And it says that the bottom side of the picture is 1.6 meters above the ground. So this is 1.6 meters and this is the ground. Okay, this is the ground. And the pin breaks and the picture falls vertically downwards. The resistive force acting on the picture is negligible. That means no air resistance, nothing. Calculate the time taken for the bottom side of the picture to hit the ground. Okay, so this is a kinematics question. Okay, so we can use S equals to ut plus half at squared. Distance is 1.6. Falls from equilibrium from rest, hence time initial velocity is going to be 0, and we are left with 1.8 into 9.81 into t squared. Now if we solve for t, which comes out to be 1.6 into 2.81, So if you solve for this, we get 0.571 seconds, which we round up to 2SF as 0.57. Okay. Now, on figure 4.2, sketch the variation of the speed of the picture with the distance fallen from its initial position. So speed against distance. From its initial position. Air resistance is negligible, okay. But it won't be a straight line. If speed increases, of course, distance will increase, but the speed, what about the speed? Variation of the speed of the picture with the distance fallen from its initial position. So initially the speed will be 0, so it will start from the origin. The speed of the picture with the distance fallen. Let's first find a relationship between this and this. How can we do that? So we can use the formula v square equals to u square plus twice as. Initial u will be 0, so it's gonna be 0 plus twice as, and the acceleration will be a constant, so we can ignore acceleration here, which means s is basically v square plus twice a, just v square. And the distance is proportional to v square. Or if we root both over, the distance, displacement actually, is equals to, if we root over both of them, cancels out, is this. So v is proportional to root over s, and whenever it's root over, it's a curve. So it's gonna be not an increasing curve, it's root over, so should be a decreasing curve. This is the same as momentum against time, which turns out to be this. Okay. Whenever a root over curve, just remember the shape, it's like this. So it is going to be the same here. There, that is what's going to be. Okay, now, for a progressive wave, state what is meant by period and amplitude. Okay, period is basically the time required to complete one wave. Or you can write oscillation actually. Same thing though. What is the amplitude? It's the maximum displacement from the equilibrium position. Or you can just write the mean position. I think it's the same. Yeah, it means the same thing. So maximum displacement from the mean position is called amplitude. Okay, now a stretch spring is fixed at both ends and is made to vibrate with frequency 25 Hz. The stationary wave is formed on the string. The distance between the fixed ends of the string is 0.96 meters. Okay, so this is given here. So on figure 5.1, draw a cross at the position of the antinode. Antinode is the maximum displacement. So either you can draw it here or here, it doesn't matter. Anything works. Now, show that the speed of a progressive wave is this. Okay, so the formula for this is v equals f lambda. Lambda is the wavelength, f is the frequency, and v is the velocity, or the speed. So the frequency we know is 25, but what about the wavelength? Okay, so there are two ways we can do this to find wavelength. There is an antinode is the lowest point, which means this is an antinode. No, I mean this is a node. Sorry, this is a node. This is antinode. This is a node. Antinode, node, Antinode. So from a node to an antinode, the distance is lambda by 4. Okay. So if its distance is lambda by 4, there is one here, one set of this, 2, 3, 4, which basically means 1 by 4 lambda into 4, which comes out to be 1. Wait a second. Distance of the total is going to 0.96. Okay, there's another way you can do this, which I think is the easier approach. So what is one complete wavelength in this? Starts from here, ends at here. This is one complete wavelength, right? And the whole wave is, you have one crest, another trough, another crest, so 3. So basically your two-third, right? 2/3 of this whole distance is the wavelength. But 2/3 of what? 2/3 of the total distance is 0.96. That is the wavelength. So what is 2/3 of 0.96? 0.64. And that is your wavelength, okay? So now we just use the formula. This into 0.64 comes out to be 16 ms minus 1, which is what it needs to be shown, and that is the answer. Okay, so the frequency of the vibrations is increased to 30 hertz. The speed of the wave does not change. State and explain what the stationary wave is formed. The frequency is increased. So if the frequency is increased, v equals to f lambda equals to v by lambda. This remains, so Vf is inversely proportional to the lambda. So frequency increases, wavelength should decrease, which means okay. So how is a stationary wave formed? There are harmonics in a sound wave. Okay. So there are first harmonic, second harmonic, third harmonic. So the formula for harmonic is frequency by n equals to n by frequency f1. So at what harmonic we got was 25 hertz, right? So okay, for which one did we get 35 hertz? First is lambda by 4, then 3 by 4 lambda. So F1 is, there's another formula, V by twice L. Twice L basically means the lambda here, which means the velocity is 16 because it does not remain changed, and length is 0.96, which is 8.3 hertz, which is the first harmonic. Second harmonic will be if you multiply this by 3, we get 24.9, which is basically 25. Okay, so the third harmonic is where 25 hertz is formed. But what about the fourth harmonic? The fourth harmonic is more than 30. It is 33. We multiply this by the first harmonic, which comes out to be 33.3 hertz, which is not 30. So the stationary wave will not be formed because stationary wave will not be formed because the frequency for the third harmonic, third and fourth harmonic is 25 hertz and 33.3 hertz. Hence 30 hertz harmonic cannot be formed. right? Because if 30 wasn't a harmonic, then the frequency, you know, then a stationary wave would have been formed. But the third harmonic is 25, or the fourth harmonic is 33, right? It's not 30, it's more than 30, it's 33. Hence, it cannot be formed. This one was pretty tricky, I would say. Yeah, this one was definitely something. Alright, now, a beam of light of wavelength 4.5 into 10 to the power minus 7 is incident normally on a diffraction grating with this lines per meter. The light passes through the grating and forms a pattern of bright spots on the string. Okay, so this is basically this the Young split experiment. Okay, so the angle formed at diffraction grating between the central bright spot and the bright spot at x is 37. Okay, which is given here. Okay, calculate the order n on the bright spot at x. Okay, so we can use a formula here. So n, d equals to 1 by capital N, and n is given here as 6 point, this part is n, and d is also given. No, d is not given, that's the wavelength. Okay, so we have to find d first. So d is 1 by 6.7 into 10 to the power 5, I think. Yeah, so which comes out to be 1.49 into 10 to the power minus 6. So now we know d. Now we're going to use the formula d sine theta equals to n lambda. Equals to n lambda. So n, if we rearrange this, is d sine theta by lambda, which now, if we rearrange, comes this by this. If we calculate this, we get 1.99, which we have to round off because it's the order n. It cannot be a decimal, it has to be an integer, so it's 2. So the diffraction grating is replaced by a grating with fewer lines per meter. Stated whether the distance between adjacent bright spot or the screen increases, decreases, remain the same. Okay. So using just the formula, n lambda equals to d sine theta, and sine theta is equals to n lambda by d. So fewer lines per meter, basically means d equals to 1 by n. This decreases, this will increase. So if d increases, sine theta will decrease. Hence, as grating d will increase, theta will decrease, and if theta decreases, the adjacent bright spot distance will also decrease. Let's erase all this. Bright spot will decrease. Now, moving on to electricity, state what is meant by an electric current. So it's basically the flow of charge, per unit time. Okay, now a cell has an electromotive force EMF 1.50 volts and internal resistance of 0.75 ohms. On figure 6.1, draw the variation of the terminal PD with the current in the cell for current between 0 amps to 1.6 amps. Terminal PD, internal resistance. Okay. So what is the formula for this? The EMF of cell is a terminal PD plus the internal resistance is 1 by R. If you rearrange this, V equals to minus R equals to minus IR plus E. Okay. Which is basically what I'm trying to do is convert this to the straight line equation, which is y equals mx plus c. So y here is V, gradient is internal resistance, and C is the EMF. So using this formula, V equals to minus IR plus E. When it is zero, when the current is zero, this will be equals to EMF, and the EMF given is 1.5. So it's gonna start from 1.5, because when I equals to 0, V equals to E, hence it's gonna be 1.5, and when I is 1.6, okay, so when the current is 1.6 R plus E, which is 1.5, internal resistance is 0.75. So minus 1.6 into 0.75 plus 1.5, which comes out to be 0.3. So at 1.6 it's 0.3. Where is 0.3? If this is 0.5, 10 boxes, each box is 0.05, 0.05, 0.05. So this should be 0.3. Oh, wait, sorry, no, it's one box above actually. This is 0.3, okay. So from here, you just have to draw a line. Okay, it's gonna be a straight line, and that is it. Simple, right? Now, next question is a metal wire X has a length. This cross-section area is given. The resistance to wire is given. The wire is connected to a circuit containing the cell in 6B. So this cell, so 1.5. And a fixed resistance shown. The current in the cell is 1.8 amps. Calculate resistivity. Okay, so formula for resistivity. Resistivity is Ra by L. R is resistance, 0.82, and area Gaussian is given 2 into 10 to the power minus 7 divided by the length. Length is 6.8 given. Just use your calculator. You get 2.41. Wait, 2.41 into 10 to the power minus 8. Round off to 2SF as 2.4 into 10 to the power minus 8. Now calculate R. How many questions are there? Okay, we're pretty much almost done. Okay, so calculate R. So let's just write down the formula as we did before. Vt plus IR. Rearrange this. Vt is E minus IR. V is given. E is 1.5 minus 1.8, which is the current in the cell, right? Into 0.75, which comes up to be 0.15. So what about I of R? To calculate the resistance of R, we should first find the resistance that the current that's flowing in this wire. So let's call this Ix, which is V by R, 0.15 divided by the resistance is 0.82. 0.15 is, we already know this from here. This comes out to be 0.183. Now subtract that from the total current, which is 1.617 amps. Now we can use the final formula, R equals to V by I, which is 0.15 by 1.617. This comes out to be 0.0927. Rounding off is 2SF, 0.93. This was in ohms. this we figured out. Wait a second, hold up. Wait, I think I might have screwed up a bit. 0.6. Okay, I think I might have done a mistake. Wait, guys, it should not be 0.027. Wait, let me see what I did wrong. Hold up. E equals to Vt plus IR. Oh, sorry about that. Just fix this back. Equals to I 1.5, 1.8. Okay. Okay, I don't know what I did wrong here. 0.75, 0.15, 0.8 minus 0.183, 617 equals to V by I. 0.0923.09. Wait, guys, let me just figure out what I did here. Oh, this is actually 0.93. 0.93 ohms, nice. Now the next question, calculate the power dissipated in the internal resistor. Okay, so P equals to I square, that is the formula. So we know the current is 1.8 whole square into 0.75. It's 2.43, round them off, 2.4. Now, describe the structure of a nuclear atom. So what does a nuclear atom have? First of all, the nucleus of the atom is very small and has a lot of space. All right, very small and is possibly charged. Wait. positively charged, and the nucleus is surrounded by electrons, right? The nucleus or just and it is surrounded by electrons, and most of the atom is empty space. Or just write empty, okay? Now P and Q are radioactive nuclei. P has 94 protons, Q has 91 protons. Each nucleus decays to form a nucleus with 92 protons. State the type of radioactive decay experienced by P. So it goes from 94 to 92, so it decreases by 2, which means alpha, because alpha is 4 by 2. So it will be alpha decay. What about state the type of radioactive decay experienced by Q? So it goes from 91 to 92, it increases. So it's going to be beta minus decay. No, not beta minus decay. Yeah, it is beta minus decay, yeah. The minus decay increases by 1, right? If it decreases by 1, you could have said it's beta plus decay, but it increases. So now the last question of the paper, guys. Particle X has a ratio charge by mass equal to this value. Identify particle X. Show your working. So charge by mass. Charge we identify as Q, and mass, let's just say M. So the ratio of this is 0.6 to the power 11. What is particle X? Okay, this seems a bit tricky. So since P and Q are nuclei, each was decayed. One is alpha decay, another is beta minus decay. And particle X, okay, we don't know nothing about particle X. We do know its mass is this. Not mass, its charge is this. So okay. Charge by mass, right? Okay. So normal charge is 1.6 into 10 to the power minus 10, while the mass is given actually over here. Wait. Right over here, guys. This is your unified atomic mass unit. 0.6 to that. Okay. So by that logic, if we divide this by 1.66 into 10 to the power minus 27, we get 9.6 into 10 to the power 7, which is not equals to this. Okay, so this is not the right way to do this. Okay, this was the charge and the mass of, I guess you have to find the particle X. So since this does not work, that means it is not a proton. It is also not an electron. And then what else could it be? How about, okay, so what options do we have? It is not a neutron. It is not a neutron. It is not a proton. It is not an electron. By alpha decay, it does not produce any other particles. By beta minus decay, it produces a proton. And what else? A neutron becomes a proton, and we get anti-electron neutrino electron, but that is also not gonna be work. This is particle X, and the charge is negative. What else could it be? Huh. Okay, so first is the fact that this is positively charged. Since this is positively charged, it cannot be electron or antineutrino or just neutrino or nothing like that. So what else is positively charged? Beta plus. Beta plus particle is positively charged, and when that decays, we get a positron. So what if it's a positron? So how do we check if it's a positron or not? So for positron, the charge is going to be the same. Charge is obviously 1.6 in 10 to the power minus 7. But this by mass. What about the mass? Positron. Okay, hold on. Let's see if I can figure this out. 1.66 into 10 to the power minus 27. This is the unified atomic mass. If you multiply that by, let's say, what is it for a positron? Hold up. What could this be? Particle X has a ratio charge mass of this. This is quite interesting. It's pretty interesting, I would say. Since it's a positively charged, it can either be a proton or a positron. Particle X, it cannot be like beta plus decay. So the only option left is positron. But even if it is positron, and you do get a mark, you're gonna get a 1 out of 2. You still have to show you're working. So we know that it's a positron, but how can we show it? That's the thing, right? Okay, trying to figure this out. Let's just read the question again. Maybe I'm missing something. Hold on. So what is a positron? Positron, there's nothing really given in the question. Positron is an antiparticle of electron. Right. It is an antiparticle of electron. So it has the same mass as an electron, but the opposite charge, right? So what is the mass of an electron? The mass of an electron... So wait a second. The mass of an electron, is it given here? Oh, it is. The mass of an electron is 9.11. Okay, that is so much simpler. If you figure it out, I think this is how you're supposed to do it. Let me see. So the mass of an electron is 9.11 into 10 to the power minus 31. So if you solve it by this, nice, yeah, we do get this value. Okay, we get 1.76 into 10 to the power 11. Okay, yeah, this question was a bit tricky, but not too hard. Overall, I would say that this paper's pattern was certainly different from 2020 to 2024. 2025 was something similar, I guess, but I wouldn't say this was a tough paper. Some questions might be a bit tricky, but overall I would not say it was a tough paper. If you guys have any questions, any queries, make sure to write it down in the comments. If you guys like this video, make sure to subscribe, like, share, comment, share to your friends who ever need the solution video. And that's about it. If you guys have any specific papers of maths and physics that you guys want me to solve, make sure to comment down below. I will make sure to solve it as soon as I can. And yeah, that's about it. Good luck for your exam at 20. I inshallah hope that all of you guys will get really good marks. Goodbye.